So ready whenever you are, Federico.
Sure. Share my screen. Can you guys see my screen?
Mm-hmm.
Yeah.
First of all, hi everyone. I'm Federico Kunze. For the ones who don't know me, I'm a core Cosmos dev, currently working on Ethermint as well as on the ABCI protocol. I've been working on Cosmos since 2018. And I started as a wallet developer using the Cosmos SDK client side. And then I transitioned to the Cosmos SDK as a developer while I was at Tendermint. And now I'm a contractor for ChainSafe working for Ethermint, which is the EVM on top of Tendermint, which provides proof of stake functionality. And it's built using the Cosmos SDK, which will provide interoperability with other zones. Let me move let me move these down here. Okay. First of all, what is the Cosmos SDK? The Cosmos SDK is a framework to develop application-specific blockchains in Go. It uses Tendermint Core as a consensus algorithm on how the overall layout of the applications using Tendermint are built is that Tendermint Core handles the networking layer and the consensus layer. And the application layer, which in this case is built using the Cosmos SDK, handles all the business logic of your application-specific blockchain. The concept of application-specific blockchain is a bit different from the ones from apps or decentralized application. An application-specific blockchain is the center of the Cosmos value proposition in terms of that zones are sovereign and that each application has its own blockchain, so that it can has its own governance, its own validator set, and that's one of the core difference with Pocket, I'd say, that each application specific blockchain has its own set of validators, and it's not shared across the different zones, which is the Cosmos lingo for blockchains or shards. So in this case, the Cosmos SDK provides the application layer, as I said, and Tendermint Core, and it's connected with Tendermint Core consensus using the ABCI, which stands for the Application Blockchain Interface, and basically sends the messages that I will explain afterwards to the Tendermint consensus in order to produce new blocks. So a little bit more about Tendermint Core. What is it? Tendermint Core is a novel BFT proof of stake consensus algorithm that provides provable liveness in partially asynchronous network. This means that it prioritizes consistency over liveness, sorry, and so it has a safety threshold of 1/3 of validators' power that needs to be instead of the half of the validators that can be offline to produce hard fork. The core logic around Tendermint is that, like in general, there can be a fork on Tendermint, but it stops the chain. It halts the chain instead of having like a fork on a live network. In case there's a hard fork, the network immediately halts. So this is due to that the feature that is the instant finality, that every block is, once it's committed, it's considered final. Whereas in Nakamoto consensus algorithms, such as the ones used on proof of stake, there's a probability that a transaction is included on a block. That's why you have to wait, for example, the confirmation time on Bitcoin or in Ethereum, which is depending on the underlying consensus used by each blockchain. Here in Tendermint, you know for sure that the transaction is finalized once it's committed to state every 7 seconds, around 7-second block time, depending on the amount of validators. So this makes it a really interesting use case for, say, supply chain logic, or whenever you wanna have assurance that the transaction is included in a block quickly. In general, Tendermint Core supports public and private chains, and it can be used for different setups as well. So how does the Tendermint BFT consensus algorithm looks like? On every new block, there is a block proposer, which is a validator that it's selected using a round robin algorithm, which proposes a valid block. Once it proposes a valid block, we're seeing here on the left side that it proposes a valid block, and then there's a pre-vote. Once the pre-vote is signed from supermajority of the validator set, that is plus 2/3 of the validator set, then the block goes through a pre-commit voting. And once that is also pre-committed by a supermajority of the validator set, the block is committed to state, and all the transactions that were on that block are finalized. If any of these voting steps is not finalized, it goes through another round. So eventually, a block that doesn't have enough validators, or that a super majority of the validators are offline for any specific reason, can take a lot of time to commit that block to state, because it goes through new rounds every time. And as I mentioned before, the SDK and the whole application layers communicate with Tendermint using the ABCI, which stands for Application Blockchain Interface. And the application blockchain interface from Tendermint Core has a set of messages that are required for the validator to check validations, deliver transactions, commit the app state, and then have an additional functionality at the beginning or at the end of each block. The first one is checkTX, which just validates a transaction, and it is required for the mempool to prevent spam transactions. It runs through each message or each transaction basic validation that, checks if the signer is there, if the sender address is correctly formatted, if the user has enough balance, if the coins are not negative, etc. It depends on the business logic, on the validation that each business logic assigns to the message, that this is run through on checkTX. Also, another important message is deliverTX, which is the standard way how transactions are, a state transition is made. It validates again the transaction, against the current state machine, and the cryptographic credentials, which can be the signatures from the validators, the signature from the sender, as well as the cryptographic credential from the validator set, and it checks that the state transition is valid. And the commit message from ABCI, it's just persisting the app state to disk. And this is how transactions are considered final. And this is the way like that instant finality is produced. After a commit message, the remaining transactions on the mempool, which holds all the transactions that haven't been that are pending, so to say, are replayed with a check TX message. And there's also a begin and end block logic, which is run at the beginning or at the end of each block. This is mostly to persist the header to the application layer context, or to, for example, on the end block to have additional, say, validator updates. So how's the life cycle of an ABCI, of these ABCI messages on a single block? Here's the application logic on the top right, which would be the SDK in our case. And there's this cylinder on the bottom, which produces the begin blocks, the deliver TX for each of the messages, and then it produces the end block. Once a transaction is delivered, it produces a transaction result for each of the messages that are delivered to the state. And then after the commit is submitted, it sends back to the application the state group, which would be the application header, the block and the block header, which has the corresponding hashes. Well, this is the consensus logic, which I explained before, that involves the pre-commit and the pre-votes rounds. On the mempool, which every time a new block, on every new block height, there is a validator that proposes new transactions, and the transactions on the mempool are validated and using checkTX to prevent spam. So we'll now talk about the SDK application components. What are the application components? Basically, there's a Tendermint ABCI application, which is the BaseApp, which is the underlying application that communicates with ABCI and sends the messages that I explained before. There's also a multi-store that is a store of key value stores. There's the application's codec, which handles encoding of state and client, and that it currently supports Amino and Protobuf. There is the model keepers as well, which are the ones that hold a key to access the module's KB store. They are secured by object capability module, which only assigns a key to the state as it requires it. It doesn't, like, for example, a module, or say, for example, in Ethereum, a smart contract wouldn't have access to others' smart contract state, for example. And this is by each module only having access to its specific KB store. And there's also the module manager, which lists all the application modules and does the wiring of them. So we'll do a bit of code analysis right now, and I'll share the code a little bit. Is it big enough for you guys to see?
Yeah, it's good for me.
Yep.
So this is how the SDK CMAP, which is like default application used for running simulations on the SDK looks like. Here we have the definition in Golang of the CMAP, which would be in, say, like the Cosmos Hub application, or the Ethermint application, or the Aragon chain application. It holds a reference to the BaseApp, the codec, as I said. Here it has two codecs before we're transitioning from Amino to protobuf. It has the store keys and the transient store keys, which I will explain later. Subspaces for that are used for parameter change proposal, the list of keepers. This is another keeper for capabilities, the module manager, and there's also a simulation manager for running simulations. So how this is initialized is you create the codecs, you set up the BaseApp with some options that you define, you set up the store keys, then each of the modules keeper. Say, for example, here the staking keeper that holds a reference to the other modules. There's the governance module here. And then you set up the module manager, which will wire each of the modules to the application. You also need to set the order for each of these modules on each block. So it will run each of these modules sequentially. Same for end blockers. And this is the same for init genesis, which is when the application is initialized the first time, say on block 0. And that's pretty much it. Here's when the KV stores are mounted, as well as the other store types. These are like generic methods. So change my screen to the keynote, if you guys can see it. So I'll talk about a bit more about each of the components. So BaseApp, as I said, is the default ABCI application used on the SDK, which runs the ABCI messages that I explained before. It also has a logger that runs the info ABCI message that is just for debugging purposes. It also contains the transaction router and the query router, which routes each message to its corresponding module handler and each query route to its corresponding module query. This runs switch according to each query route or each message type. And then they run that message specific logic. The BaseApp also holds the Tendermint consensus parameters, which can be changed for each application and through governance parameter change proposals, such as the block, evidence, and validator parameters. Say on the validators, you can define the type of the keys that each validator will support. By default, it uses a Tendermint SecP256K1 curve. On the block, you can have the average block time if you want to produce empty blocks or not, and with the evidence, the types of evidence that are supported. There's the BaseApp also defines the database that you're using and the logger that is used to for the info ABCI message. And it also holds a reference to the anti-handler. What is the anti-handler? The anti-handler is the logic that it's run before the transactions is actually run. So when you send a transaction, it goes through deliver TX message, as I explained before, but during that, it also runs the preset checks necessary to, besides the message validate basic, to check if the, for example, the gas consumption is enough, the signature validation is valid for a corresponding validator set. Say the user has enough balance to pay for the message fees, all that. So we'll now do a little bit of code analysis on the BaseApp. I'll do, let me share my screen again. Are you guys a bit lost? Just to see how it's, if you guys are understanding. So here's the BaseApp definition. As I mentioned, it contains a logger, the database, the commit multi-store, which is like the specific, the concrete type of multi-store that is used to on the SDK. It has the router for the transactions, on the query router for the queries. Also has a transaction decoder for the clients. And it also has the anti-handler, as I explained before, that runs on each message. It also contains some volatile state, the check state and deliver TX state that are specific for the check TX and deliver TX messages. As it says here, the check TX, the check state is set on init chain and reset a commit, and deliver state is set on init chain and begin block and set nil on commit. So basically it resets this volatile state on every block. Here's the parameter store for the consensus parameters. These are the minimum gas prices that are defined by each validator. So a validator can define that it accepts 0 fees, and then the whole network can accept 0 fee transactions as long as that validator is a proposer. So if you set a transaction and the validator has not much voting power, your transaction won't be included on a block until the validator that supports 0 fee transactions is a block proposer. This is halt hide and halt time for upgrades and hard forks. So when you want to upgrade a version of your application to another version, you can set a halt hide, and your application will stop at that hide, and then you can run the upgrade, and they will restart the new application with a new version on the hide afterwards. Here the important part is the router that sets the renew routers to the handlers. The ABCI logic, that is basically the BaseApp is the ABCI application that connects to Tendermint. So here's the init chain, which is run at the very beginning of when the chain is initialized. There's the info for logging. There's the check TX, which runs the validation of transactions. There are 2 types, which one is when check TX is run for the first time, and the other one is when check TX is run for following times. So it runs the transaction on check TX mode, and for deliver TX it does the same, but with deliver TX mode. So when running the transaction, you will know if the transaction needs to be persisted to state and the state transaction needs to be actually committed to state, or if you only need to validate the transaction like sort of like simulation. And then the commit is when you persist the application to state. So I'll share again my keynote. So now I'll talk a bit about the multi-store. The multi-store, as I mentioned, is a store of key value stores, and each module contains a key to one or more key value stores. There are multiple databases supported by Tendermint. The default one is GoLevelDB, but you can also set your database to use like ProxyDB, VaultDB, or others. And as I mentioned before, the application state is specific to this on the commit message. There are multiple types of stores. The most important ones are the AAVL store, which is the default one that uses the IAVL tree, which is a self-balancing binary tree. And those trees are, those stores are wrapped into like one or more specific store types. For example, you can have an IAVL store wrapped as a gas store keys, which will consume gas according to the level that you want on each read or write up operation. Or you can also wrap an AVL store with a prefix store so that you can have only a subtree of that specific IAVL store. Or you can also wrap the same store using a cache KV store for caching logic. So here's how like a general block and transaction lifecycle works. As I mentioned before in the diagram for ABCI, it runs on every block, it runs begin block, then for each transactions, it runs deliver TX. Finally runs the end block logic, and then the commit that persists the transactions to store and then are considered finalized. So on begin block, it sets a new deliver state, like volatile state with the previous header, with the current block header that was produced after the commit phase on the previous block. And then it runs begin blocker for each of the modules in the order that you define on the module manager. So on check TX, it runs run TX, getting a context for that specific transaction for check state, and then it runs the anti-handler and then each of the messages. So on the anti-handler, as I mentioned before, it will check that the signatures are correct, that the balance of the user of the first signer or the sender of the transaction is enough to face for the fees. It implements the sequence or the nonce for the transaction for the sender, and then it runs the messages, but without actually performing a state transition. Deliver TX is the same, but unlike check TX, we execute the messages that result in the state transitions. And then on the commit phase, all the deliver state is written to the cache multi-store and to the respected commit store. For example, the AVL store or wrap AVL store with such as the gas KB store. Then the multi-store writes to the database. And then you set again the checked state with the header and reset the check state and then set the deliver state to nil. I'll be quickly with this code analysis because it's like one of the most important part of the BaseApp. But there are so many messages that I want to just so second. So I guess I'm sharing this one. Here's runTX, which runs each of the transactions in the specific mode that you can define here. First, it gets the gas info from the block that is for the block. And then the important part is here. It runs validate basic for each of the messages. So you can define a message on, say, so for example, if you want to send a transfer, a message send, you can define its validate basic for the specific send message. So check if the sender address and the recipient address is empty, the amount is valid, and the amount is all positive. So it runs all those. So it runs all those checks for the messages, as I mentioned before. Then it runs the anti-handler, which checks for the gas consumption. As I mentioned before, it returns the events from the anti-handler, and then it runs the specific messages on either checktx or delivertx mode. So here, if transaction mode is deliver, then you write to the cache multi-store. If not, you just return the info, the error, and the gas info associated. So on run messages, you first get the route to use the application router, and then you get the specific handler for that message. You run the transaction using the handler. You get the events, and you set the events to ABCI, and then you return a transaction result, which contains data, logs, and events. So that's basically the transaction lifecycle, how it works in Cosmos. The application also contains the like a custom SDK application contains the keepers, which are basically gatekeepers for a given KB store and are usually associated with a single module. They hold the reference to the store key, and they also have a codec for encoding and decoding types to and from the store. This codec, as I mentioned before, can use Amino or protobuf. They can also hold a reference to other module expected keepers. So let me show you real quick here. So I'll show you how keeper looks like. So this is, for example, the fee distribution keeper. It holds the store key for that specific keeper, contains the codec for marshalling or unmarshalling. This one is protobuf one, and it contains the account keeper reference, the bank keeper reference, and the staking keeper reference as interfaces. So you can see here the expected interfaces that the function that it will use for the account from the account keeper, such as get account, set account, from the bank keeper, get balance, and then staking keeper, like get all the validators, / jail and jail on the delegation. Share screen again. Also for modules that, so in Cosmos, there are parameter change proposals so each module can have its own parameters. For example, the bank module that handles logic and accounting for accounts has a parameter that was initially set for the Cosmos Hub that was preventing users from transferring tokens until we knew the chain was mature. So you can have that as a configurable param, and then you can submit also a parameter change proposal to change each of those parameters. So there's also the module manager, which manages collections of application modules. You can define a common interface that modules need to expose. You need to register the client for REST and CLI, the routes for the transaction and queries, as well as the handler and querier, the ABCI logic, init chain, import, export, genesis, begin, and block for each of the module, and then the module invariants, which are checks that need to be asserted on every block if you are running a mode on an invariant mode full node. So an invariant node is basically, say, you have a tracker that uses supply, and you know that the total amount of supply is the sum of the balances for each account. So you have a passive tracker, and then you have the actual sum of the balances that are within each of the accounts. So an invariant modes run the invariants that it iterates over all the accounts, sums their total amount of coins, and it compares it with the total supply of the chain. That would be a supply invariant, for example. If you're running a node that runs on invariant mode, your node will be super slow, but it will verify that those invariants are set on every single block. I'll skip this to go through the modules, and then we can take another look to the code. So this is the centerpiece of the Cosmos SDK, which are modules. The modules are the ones who implement the core business logic of an SDK application. Think of the module as a smart contract on Ethereum, for example, or a smart contract on Tezos. So they're usually located on the X/ folder that stands for extensions. When you're writing modules, you need to have some key considerations. One is composability, that an application needs to be composed of different modules. Specialization, that each module needs to be specialized on only a single thing. So we had the bank module that handles supply and accounting for balances. And we also have the staking module, for example, that handles how the proof of stake logic works on the SDK. And these modules are secured using capabilities that each module has a reference to a single KV store key. Their components are the application module, which is the key component and also of the module manager, the handler, ABCI logic, keeper, query messages for running transactions. A transaction is basically a collection of messages. So you can have like multiple messages that perform different state transitions in a single transaction. You also define the REST and the CLI clients, as well as the types that are specific to your module. Say, on the staking module, you can define your validator type or your delegator type for proof of stake. It also has some invariants that are the assertions that I mentioned before. Module genesis, store decoders, and message operations for the simulator. So the simulator is a nice feature that we implemented on the SDK to run fast testing of transactions. So you basically generate a random genesis JSON and you run state transition with randomized transactions. So you can actually check if your, say, if your application has an non-determinism, or that the export and then import logic is wrong, or that there's a panic that will potentially halt the chain. It comes very handy when creating applications on the SDK, and it's really easy to set using the module manager. I'll run into some like a very concrete example of modules on SDK before we jump into a specific module. And I wanted to talk about Ethermint, which is a project we're working on with ChainSafe. It's related to the project of Aragon chain. So Ethermint is technically the EVM from Ethereum running on top of Tendermint, which will provide the same functionalities on Ethereum, but on proof of stake. It also will run on fast finality, which will open a new variety of opportunities for smart contract developers that need to run supply chain logic, for example, or different set of DeFi applications. It's built using the Cosmos SDK. It's interoperable using Ethereum smart contract that can run delegate calls around them, and we'll also have cross-chain contract calls. So if you're running the like the Ethermint application and you deploy your smart contract to Ethermint, you will be able to submit an ABCI cross-chain delegate call to the native Ethereum that it's running on mainnet, and you could call a specific function on Ethereum from Ethermint, or on a PEX zone, through a PEX zone or a bridge such as the chain bridge that ChainSafe is working on. So the concrete example will be Aragon chain, which will be like another application-specific blockchain using the EVM module. So the EVM module, which is the one that implements the EVM on top of Tendermint, can be also used by other blockchains, as like in the same way like application-specific blockchains can use a staking module from the SDK. And it will have, as you can see here, Solidity, Truffle, MetaMask functionality with Web3 compatible on IBC. So the Cosmos SDK, you can build basically whatever business logic you want and connect it to Tendermint in an easy and friendly way using modules. The ones in blue are the ones that are native to the SDK, and you can implement other modules and write them up to your Cosmos Cosmos SDK application-specific blockchain. There's also WASM contracts that are going to be deployed to the Cosmos Hub, the EVM module that is going to be deployed in Ethermint. There's auctions on stable coins that are being used by Kaba, NFTs, there are NFT modules, oracles and prediction markets. You can implement all those sort of things using modules. So in general, the SDK is modular, scalable. By using modules, Tendermint the consensus algorithm that can support thousands of transactions per second, and it's also interoperable because it will use IBC. It's secure because it's secured by object capability model, and the simulation that runs randomized transaction uses proof of stake. Each application-specific blockchain is sovereign, so you can use governance for their specific needs. It's open source, written in Golang. I will share my screen to just take a peek into a module, just to show you how it looks like. So we'll take a look into the evidence module here. Take a look into the module.go. It defines the application module by basic, which will define the codec if it uses Amino or protobuf. The default Genesis state for that specific module, the validation for that Genesis state, registering the REST and CLI client routes and transactions, and query routes. And then you define the module keeper here with its router key for the handler, which is basically the name of the module. Same for the query route. The handler that runs each of the transactions, the keeper that runs each of the queries, the init genesis for ABCI, the export genesis for ABCI, begin block, which is the logic that is run at the beginning of the block, and end block, which is run at the end of the block, which can contain validator updates for each of the, if you need it. Here's the simulation setup that you can define a random Genesis state, randomize governance proposals, stow decoders for decoding the module state, weighted operation, which is in this case are set to nil because this module doesn't have this part wire up yet, but you can define here the messages that will run randomly. So the most important part of the module is the handler and the keeper. The handler will run each of the transactions that have a specific message type. So in this case, if you have a message that is submit evidence, you'll run it to the submit evidence method from the keeper. Once it's successful, it will emit the events that the state transition was successful, and you'll send it to the application as a result with the data on the specific events. So here's the keeper that I showed you before. Every keeper contains a logger for the ABCI info. It has the router for the, also for registering extra routes for different evidence types. And if you want to submit an evidence, here's the business-specific logic that I will not go deep into it, but the important part is that you can get and set things from the store here. So this keeper specifically uses a prefix store that is prefixed by a specific key here. So you get the KB store using the store key from the keeper. You wrap it on the prefix store and you set it to the prefix that you want here. Then you just use get or set here with the key in bytes on the bytes for the specific value. And this is why each of the keepers contain a reference to the codec for encoding and decoding of those types. So I'll look into Marshall and Marshall. So you can unmarshal from the bytes that you receive here into a concrete type. Same goes for JSON and from a type to bytes for marshalling. I'll start here. So that's a general overview of the SDK. If we have time, or if you guys want to stay more, like I'm open for questions. Otherwise, we can continue a bit more on a short intro to like IBC. Colin?
Yeah, thanks, Federico. We definitely have time if anyone has questions.
Or would you want to go through something again that you didn't understand, or how difference, like what's the value proposition of Cosmos in general, or something?
All of it was really interesting. I'm trying to think of.
Or something specifically for Aragon, the Aragon project, or Ethermint.
I mean, I'd like to hear more about Ethermint since we'll be getting more into that work soon. I don't know what everyone else thinks.
Ethermint, I think, is more of the focus. So that
Everyone?
The Ethermint is probably more of the focus. So it would be nice if you can walk through some of the tests. That part that you showed about the modules, that was very interesting as well, the EVM, how that works.
Sure. So I can, wait, I need to, so take a look into the application in general for Ethermint. So the Ethermint app, as you can see here, it's basically the same as the CMAP that I showed you. Defines the BaseApp, the codec, the keys, the same keepers, as well as the EVM and the faucet keeper that is for testnets. Also the important part for the Ethermint application in general is that it has a different anti-handler. So I'll show you here how anti.go. So an anti-handler basically runs the the pre-checks before actually running the transactions, it uses decorators, which are specific. It's a decorator type for running things sequentially. And it uses a different one from the SDK because it needs to run different pre-checks for Ethereum transactions. So here you have a setup decorator, which is to set up the an infinite gas meter, because the anti-handler also consumes gas, and you need to basically spend the same gas as the as Ethereum. And the specific checks for the anti-handler is that the user has enough fees. The signatures from the message are valid. The chain ID from the app is correctly set to be an integer. And then it also checks for each of the that the balance is enough to pay the gas cost here, and then increments the nonce. Then here is the gas consumption logic, which is the core part here, because it runs on Ethermint Core. Sorry, on gas core, and it gets the intrinsic gas from it, which is run differently from the SDK in general. So that's the main difference with the anti-handler from the SDK, and also I'll run into the EVM module. So the EVM module contains two different message types. There's one Ethereum transaction type, and then is one message Ethermint type. The difference between them are that this is run on a standard transaction running the on the default anti-handler logic, and this one is run using the custom Ethereum logic. So the one that is used the most is the message Ethereum transaction. That is the one used for smart contracts. It's verified the signature and retrieves the sender, and it runs a state on Ethereum state transition using the data from the transaction, as well as the reference to the commit state DB from the keeper, and the sender, which is in a different it's in a different format from the SDK, so we need to retrieve them from the command bytes of the address. Then it runs a state transition from the EVM, sets the transaction logs, and then it emits the specific events that will be used for the WebSocket and the event subscription. So if we take a look into the keeper, it has different, like it has a pot key and a commit state DB. It has the transaction count, which is required for the EVM. It's reset on every block. And here are the setters for each of the this. As you can see here, this KP store is not wrapped into a prefix store, but it still uses the gas KB store, which is the default on the SDK wrapper. And here, the state DB calls the specific methods from the commit state DB, which is the one used by the EVM. So say add balance here. I'll run into state transition first so we can see how the lifecycle works. So when you run a state transition on the EVM, first you guess the intrinsic gas, you set it to the gas meter, then you update the accounts, you create the new EVM, and you create the new EVM from the context. And then you either create a new smart contract or you call a specific transaction. Then you update the node for the state transition. And then you return the result data with the blown filter, the EVM logs, the return value bytes, and the transaction hash as well. And this is basically what the EVM call or the EVM create calls from the state DB. So according to the message, you will call, say, add balance to a specific state object, or subtract balance, set different node, set the code specifically, or on the different sort of methods supported by this interface that is here on Ethereum. But it's the required one for the EVM. Create account, sub balance, add balance, get balance, refund gas, suicide. And then this is like an iterator over the address for the storage. So on the specifically on the state objects, it's also an interface. It's the same interface that it's used on the EVM with slight modifications to support the Cosmos SDK. So that's why, for example, it uses the account from the SDK. It has an account address. And these are the specific methods that are supported by the state DB for each of the application, for each of the state objects. So add balance, subtract balance, and then you set it to state object, for example. State. Yeah, and that's pretty much it. It's mostly wrappers, like supporting the right interfaces and calling the state transition without those interfaces using the concrete types from the SDK.
Nice. Pretty good. I'm very curious about the, we have some tests here that are simulation tests recently introduced.
Yep.
Could you a little brief about that?
Sure.
Like the import and like custom genesis fast. There's some of them here that takes quite some time. I try to run them.
Yeah, so it depends on how much, so by default, the blocks are in average like 6-7 seconds. So if you run them for a number of blocks, it will take definitely some time. Wait. So came back to the SDK to show you how the simulation works. So here is the staking Genesis for simulation. It basically creates a randomized state for each of the Genesis fields from the module. So if you go to the staking Genesis state, it has the parameters, last voting power, the validators, the delegations, the unbonding delegations, the read delegation, and a flag that is supported or not. So for each of these fields, you need to create a randomized Genesis state. So here, say the unbonding time for the parameters, you set it to a random value. Same for the maximum validators. And for the validators as well, you get, and you set the commission for them. You can create a specific delegation for the validators or not. Then you set it to this randomized Genesis to the state. Another important simulation functionality is running operations in a randomized way. Here you define, so each operation is basically a message with a weight. So on every simulation step, it will check if the operation has the like randomized selects a number between 1 and 100, and if it's lower than the weight that you define here, it will run the transaction. So you define the default weight for this specific message type, and then you simulate each of the messages. So, for example, we're simulating here, create a new validator. We get the validator, check if it's found. If it's not found, you need to create one. Then you get the balance for that address, for that simulation address that is created on the simulation initialization. You select a random number from the address balance, and then you create a self-delegation for that validator, create a new description with whatever string you want, say for the moniker, identity, website, whatever. Then you set random commission rates, and then you create the validator, and then you submit it through app delivered TX. So you can actually run the state transition. So this runs into the BaseApp anti-handler, and it writes it to the state and then commits the transaction. Yeah, so it runs a full transaction lifecycle with the random values that you define for the message. Same for, say, delegate. You get random validator set, like a random validator from the set. And then you as a delegator get a random value from your balance. And then you get a random value for the fees that you will submit the transaction with. And then you create a new message delegate from your address to the random validator that you got, and with the random balance amount that you got as well. And then you run application delivered TX. So that's pretty much it.
Oh, nice. That's very complex. It's a huge testing tool.
Yeah, it's so the most important things that helped us to like squeeze bugs on the SDK prior to the Cosmos Hub launch was basically the like implementing as a simulator for staking and distribution ownership. So it's really interesting to just see how it goes, and if you can set like different parameters on different messages. If you can get it through if you can get your application through a simulation setup, and it runs it through full simulation without any complexities, then basically you could say you're almost bug free, and you will not panic with just the default setup for your module.
After the simulation runs, is there a way for you to quickly analyze the block structure to see about the forks and
yes,
to have
so
visualization?
The simulation, so you can define parameters for the simulation as well, say the amount of blocks that you want. You can also define a custom genesis. So if you say you're preparing for mainnet launch, you got your genesis state from the real validators that will run on mainnet. You define the parameters for each of the modules, and then you can run a full simulation using that genesis. So you know that you can define randomized messages for that specific genesis state that you will use on mainnet. You can also check the logs for each of the messages, see how many of the messages were run. Say you run like 100 create validator message, or you define or you created like 1,000 message Ethereum transactions, whatever, and you have statistics for each of these messages, if they were returned with error or they were called successfully. And you will also get, if the simulation fails, you'll get the specific message that was the operation on which block, on the error message that was fetched from that panic. You also export you the genesis state. It will also export you the state prior to when that failed occurred. So you can, when you fix the bug, you can rerun the whole genesis from the block height before, and you can continue the simulation and see if it passed or not.
Oh wow, that's pretty nice. So it really aids on the testing, like daily testing.
Yeah. So if you want to run an upgrade on your application, say I changed the encoding format from Amino to protobuf, and I implemented new features that are breaking changes. I need to upgrade all the full nodes from and all the validators need to upgrade their version of the application. It will also simulate the export and import genesis. So when you export, when you upgrade, you basically need to export the current state into a new genesis file, and then you upgrade, and then you need to import the genesis, the new genesis file in order to restart the application. So that simulation is also supported.
Is there a way to see after you run the simulation? I would like to see a visual graph of the blocks and which block is following which block to
no, there's no UI. There's no UI for it, unfortunately.
Then identify the forking, for example. Let's say
because the simulation will immediately stop on the block that the failure occurred, and it will export the state on the previous height.
Okay, so that when there are failures, you get
It automatically stops.
okay, and then
So-
from there you have to manually check the logs and things like that.
Yeah. So this is how the standard simulation works. On the SDK, we have a tool that's called RunSim that you can define seats, different seats for the simulator. So each seat will run a different, will create a different Genesis state, and it will create different messages from that specific seat. So you can recreate. So for example, some seats might successfully perform the simulation, and some seats may fail as well. So it's better because you can run your whole application using different seats instead of just one.
Is it possible to use this simulator with the Aragon smart contracts? Let's say we make a simulator that starts the chain, deploys all the smart contracts that we are interested, and then perform actions, random actions into them. Would it be possible to?
Yep, you will need to create the operations with the specific bytecodes for the smart contracts for the Aragon chain source. The current bytecode from the Aragon smart contract that you want to simulate. Say, and then run specific, like set the data to the specific calls from the Aragon contracts to other Aragon contracts. Yeah, you can technically do that. I'm not very familiar how to do it, but you can do it.
Okay, and do you see value on this, and how much effort that will be?
As long as you can express the contract calls on the state transitions into Ethereum transaction data, you can simulate whatever you want.
All right, we gotta wrap up in about 5 minutes, but if there's any last minute questions, we can take them.
Yep.
Oh, I'm happy. This was really good.
Awesome. Yeah, that was amazing, Federico. Thank you so much. And thanks everyone for coming. And I'll post a recording as soon as it gets rendered.
I also got some slides for IBC. If you guys want to take a look into this.
Well, would you be interested in doing another presentation in the future sometime?
Yeah, for sure.
Yes. Yeah, I mean, talking through them definitely adds a lot of value. So maybe we can schedule one in a few weeks or something.
Yep.
Awesome. Well, thanks again. Happy Monday, everyone. Enjoy the rest of your days.
Cool.
Thank you, Federico.
Bye, everyone.
Talk to you soon.
Bye.
Bye, thanks.